All right, section 9.1. Today we're taking a look at sequences. And you know what a sequence is. You've seen sequences since probably somewhere in junior high is where you're first encountering them. And we're going to define them a little bit more formally than you would do, with a 7th grade class. And they look something like this. So a sequence is a function whose domain is the natural numbers, where natural numbers are your counting numbers, 1, 2, 3, 4, and so forth. Though subscript notation is commonly used. So the values a1, a2, ... are the terms of the sequence. An is the nth term of the sequence. Okay, so the subscripts are the natural numbers. We're going to use this notation. This is very common notation. And the first one we're going to take a look at is finding 5 terms of a sequence. So you have, in essence, a formula given to you that tells you how a sub n is defined. It is 4 over n factorial. And so if we're wanting to do a1, then we're doing 4 over 1 factorial. And 1 factorial is just 1. So this is the term 4. A2 would be 4 over 2 factorial. So what is 2 factorial? Not just the value, but what does it mean? 2 times 1. Okay, so that's factorial notation. It is just 2, right? So this is just 4 over 2, or it's 2. A3 would be 4 over 3 factorial. So 3 factorial is 3 times 2 times 1. So this would be 4 over 6, or 2/3. We're going to do this 5 times, so we're on A4. A4 is 4 over 4 factorial. You can't just cancel those 4s. This is 4 over 4 times 3 times 2 times 1. You can cancel the 4s here if you'd like without simplifying. Then this would be 1 over 6. And then A sub 5 would be 4 over 5 factorial. This is 5 times 4 times 3 times 2 times 1. The 4s will still cancel, but now instead of 1 over 6, I have 1 over 30. And if we were listing this as a sequence, we would just write them in order side by side. So we would have, I don't want to do parentheses, I've got 4, 2, 2/3, 1/6, 1/30. And these are the first 5 terms of the sequence. Okay, so far so good? Pretty straightforward stuff. We're going to take a look at some calculus ideas that are associated with limits, or with sequences. And the first one is limits. So we're going to let L be a real number. The limit of the sequence a sub n, and notice they do put that in curly braces, is L, which is written, the limit as n goes to infinity of a sub n equals L if. So let's check on some math notation. Do you know what this symbol means? I think we've encountered it together this semester.
All.
For all. Yes, this says for all. And then we see some things that we've seen before in calculus classes before. For all epsilon greater than 0, there exists a capital M greater than 0, such that a sub n minus L is less than epsilon whenever n is greater than capital M. All this is telling you is that if your sequence gets long enough, you go far enough in the sequence, the distance between the limit and the sequence value that you're at is getting infinitely small. Those values are getting infinitely close together, closer and closer and closer within epsilon, and epsilon can be any value, so you can make it as small as you'd like, but it's positive. And then it says if the limit of the sequence exists, and sometimes they don't, but if the limit of the sequence exists, we say that the sequence converges to that limit. If the limit does not exist, then we say that the sequence diverges. And so just a real quick, easy divergent sequence is, let's just say you had the sequence where it looked like this, n, which would be the sequence 1, 2, 3, 4. It's just the natural numbers. This is a divergent sequence, right? It doesn't approach any specific value. Agreed? So this one would diverge. And let's do a real quick, easy one of one that actually converges. We can do 1 over n. So if you do 1 over n, you're going to have 1 over 1 and 1 over 2 and 1 over 3 and 1 over 4. And while we haven't exactly established for sure that this really converges, I can tell you this will converge. And can you have any idea what you think the limit should be? Looks like it's 0, right? Okay, so we didn't prove that, but intuitively that makes sense to us. Everybody with me? Okay, so these are sequences. Now, things are going to change when we get to 9.2, and we're going to be looking at series, and that's a different thing altogether. Although it's related to sequences, this second one that I just wrote up there is actually going to diverge when we look at series. Okay, so series and sequences don't have the same properties in terms of convergence. But right now, this is an example of one that diverges, an example of one that converges. Now, there's some limit properties, and these limit properties are going to feel a lot like some of the different properties we saw with limits when we were looking in Calc 1. Okay, so here's a few of them. So if you take the limit as n goes to infinity of a sub n plus or minus b sub n, this is the same as the limit as n goes to infinity of a sub n plus or minus the limit as n goes to infinity of b sub n. Okay, and because L is what they're identifying as the limit of a sub n, and we have plus or minus here, so let me put it that way. K is what they're identifying as b sub n. This would just be L minus K. And I'm just getting that from up here. The limit is L, and this one's limit is K. Okay, so you can separate them out. We did that with limits of functions. Okay, we did the exact same thing when we did functions back in Calc 1. All right, the second one is that the limit as n goes to infinity of C a sub n, okay, is going to equal the same thing as moving the C in the front. The constant or the coefficient can move out in front. And this actually, that's not an n, that should say a sub n. And then this would be C times L. So I can move the coefficient multiplier, the constant multiplier, out in front. And this works for all C values in the real numbers. Okay, so all C values that are real. Positive, negative, it works for 0. Rational, irrational, doesn't matter. All of them work just fine. The next one talks about what happens when you multiply them. Okay, so we have a sub n times b sub n. What do you suppose happens? It's the individual limits multiplied, right? You bet. So this is the limit as n goes to infinity of a sub n times the limit as n goes to infinity of b sub n. And those limits values are called L and K here, so this is L times K. So if this is, I hope this is feeling familiar. I shouldn't say if this is feeling familiar. I hope this feels familiar. We did this. We did it twice in Calc 1, for those of you who actually had my Calc 1 class. We did it when the limits were finite, like L and K, and we also did it when we talked about things that were infinite and how it played out, and they worked the same way. 4, this is the last one here. The limit, any idea what we haven't covered? Division. So we'll do a sub n over b sub n. So what do you suppose is going to happen? They act the same way. Limit as n goes to infinity of a sub n over the limit as n goes to infinity of b sub n. It's going to be L equal to L over K. We do have the condition that we need the b sub n to not be 0, and we need K to not be 0 for this to actually hold the way that it's written. We will talk about what happens if, in fact, this limit down here does equal 0 and how that plays out later. But the purpose of the definition here, in order to divide them, we need to have actual numbers that are not 0 to do that. So we have those here. Now, the one place where these kinds of properties, where we could just separate and do independent pieces and then either multiply or add or subtract or divide or whatever, did not work for us is when we did derivatives. So there was a place where we weren't able to just do that, right? So the product of the derivatives is not the same as the derivative of the product, right? So you can't do this just with all kinds of things, but you can do it with limits, and you can do it with limits with sequences, just like we did it with limits with functions. So we're going to decide whether or not certain sequences converge. And if it does converge, we're going to find the limit. And it's a very interesting way that you describe this, because this is how it's always described. It says, decide if it converges or diverges, and if it converges, find the limit. But the way that we actually do it is we attempt to find the limit. And if we're able to do so, then it converges. And if we're not able to do so, that diverges. So although the directions are written this way, we do it backwards because that's the way that it's defined. It's defined to converge if the limit exists. So we attempt to find a limit. Now, there's a lot of properties that you have seen used before. The properties are going to be the same properties we used back in Calc 1. So for example, on this one, what we want to know is we want to know the limit as n goes to infinity of 3n cubed minus 1 over 2n cubed plus n. That's what it says. But we did this before. We just did it with x's where the n's were. Now, there is a difference. X is a continuum, right? The domain is all real numbers. N's domain is actually just natural numbers. But that doesn't change the way that limits work. They work the same way. So this is what we did back in Calc 1. We said, hey, there's an n cubed, and I'm going to multiply by 1 over n cubed on the top and the bottom. And what that does, of course, is distribute everything through here, is to create some of these that give you numbers. So 3n cubed times 1 over n cubed would just be 3. The next one will be 1 over n cubed. On the bottom, I have 2n cubed times 1 over n cubed, so that's 2. And then I actually am going to get plus 1 over n squared. Okay, nod your head if that looks familiar. I know it's been like a year. But does that look like something you've seen before? I hope it does. Because the whole idea is that you have the ability then to separate all the limits out. I'll write it this one time and then I'm never going to write it again. What actually happens from those properties that we just had is that we're actually able to separate this and say, okie dokie, I'm going to do the limit as n goes to infinity of 3 minus the limit as n goes to infinity of 1 over n cubed over the limit as n goes to infinity of 2 plus the limit as n goes to infinity of 1 over n squared. That's what those properties on the previous page said we're able to do. Well, we've learned what the limits are when we're working with individual constants. What's the limit of 3 if n goes to infinity? It's 3, right? It stays 3 the whole time. In terms of a graph, it would be this constant y graph, right? Y equals 3 graph. It's 3. What is the limit of 1 over n cubed as n goes to infinity? That one is 0. What about the limit of 2? 2. And the limit of 1 over n squared? 0. And we get a very last total then of 3/2. Okay? All the properties work the same way. And this is sort of what's hidden behind the scenes right here as we're doing them. And the way that we usually notate this as we're working, because we don't write out the part that I just squared in yellow, we do this. Remember doing that? We're showing that those pieces go to 0 and the pieces that are left, the 3 and the 2, are ending up being our limit. Now 3 is not a polynomial over polynomial. Okay, so we can't just do it in the same way. So let's take a look. We're going to do here the limit as n goes to infinity of minus 2 factorial over n factorial. So what's going to be helpful to us is to write out some of this factorial notation. Okay, we'll start at the bottom because that's the one that we usually think of as being the natural n factorial that definition. What is n factorial mean? Or does n factorial mean? What do you multiply n by?
Every number before n.
Every number before or below, right? Smaller. So what would be the next one? Yep.
Times n minus 2.
N minus 1. You got it. All right. We'll write out a few of them, and then we're going to put dot, 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 3, 2, 1. Cool with that? How about the top? What would n minus 2 factorial be? Don't overthink this.
It would just be the same thing as minus another factor.
Okay, so it'd be the same thing, but the starting point's different, right? Where do we start?
n minus 2.
N minus 2.
That'd be n minus 3. N minus 4.
Yep. And do you see some of these matching up? Yeah, in fact, the entire numerator matches up right here, doesn't it, with the denominator. So this leaves me with the limit as n goes to infinity of 1 over, and you can either multiply it out or you can leave it in factored form. I'll multiply them out. It's n squared minus n. What happens as n goes to infinity with this denominator? Yeah, the denominator is going to go to infinity, and then 1 over something that's getting infinitely large is going to be 0. This is 0. So in each case of these two on the screen, I found the limit. And what that means, since I'm able to find the limit, is that it converges. Notice we didn't need to know it converged to find the limit. We attempted to find the limit, and when we were able to do so, now we know it converges. There's one more before I switch slides, though. Are we okay? Yep.
What were the properties for infinity with limits?
I feel like we might be finding one in a minute. So give me an example of what you mean.
Like if we had infinity over a set number, would that just be infinity?
It would,
And
yeah.
Infinity over infinity would be 0.
Yeah, so if you have infinity over infinity, it means that you need to simplify something in order to be able to tell. Because if something is infinite divided by something else that's infinite, because that's actually what's happening on number 3. We had to simplify the algebra to figure out what's going to sort of cancel itself out. And depending, like if this fraction on number 3 had been flipped upside down, this would actually not converge, and it would be an infinite value as n goes to infinity. But because of the direction of the infinity over the infinity with the algebra simplification, we see that the denominator becomes infinite after we've reduced, but the numerator is constant. So I think what you're looking for is something like, I'll write it at the top, something like this, where if you have the limit, and if you've reduced it, the limit of, we'll call it a sub n, and this is actually infinite over a number, then this is infinite. If it is a number over infinity, then it's 0. And these are terrible. They shouldn't say equals. We'll fix them. Right, we approach those values. If you have infinity over infinity, then you need to reduce to figure out what happens next. If you have a number over 0, this tends to infinity. If you have 0 over a number, this one would be 0. Obviously, if you have a number over a number, it's fine. I think that I've covered all of them. Does that look okay, Ben?
Yes.
Can you think of any of the ones that I haven't mentioned that you're not sure on?
No, it was mostly just infinity over.
Infinities, okay, yeah. Yeah, the key is that if you have something that's infinite or something that's infinite, you've got to find a way to reduce them. Or you may just not be able to do so, and then the answer is that you don't know, or you can't tell based on the work. Yeah. At least not from the standpoint of what we're doing here. There's other standpoints sometimes where we can. Yep.
Do the properties that we had before with like the exponents where you could like figure it out super quick still apply? I don't remember what
You're
they
thinking
are.
about what happens with asymptotes, horizontal asymptotes, where if the degree on top is smaller than the degree on bottom, then it's going to be, and it's going to have an infinity essentially on bottom, and it'll be 0. Yeah, all that still applies. I'll let you go and look those up if you would like, but yes, they still apply. Mm-hmm. Yeah, and what you're looking for, if you're looking for it, like in your notes, is we talked about it in terms of horizontal asymptotes.
We did that
Yeah.
in chapter.
I think it's in chapter 2, because that's where limits first encounter, where we first encounter limits in this book. Yeah. Okay, we have one more. And here's a really good example, actually, that does not work to simplify, Ben. So you mentioned the question, and now we've got one. Right now, on top, this sign, as in, it does not approach a specific value. You know what sign graphs look like, right? Yeah, they're waving up and down. But the kicker is they are trapped, right? They don't go infinitely high or infinitely low. They're trapped between what values? 1 and -1. So whatever they are, they're bouncing up and down between 1 and -1 and everything in between, right? But what's the denominator doing?
Infinity.
It's going to infinity. So even though the numerator doesn't go to a specific number value, we do know that it's going to be something between -1 and 1, correct? So what happens when you divide any of those numbers, even if they don't always stay the same, by something that gets infinitely larger?
0.
It's going to go to 0. So this actually does have a limit of 0. So we're going to write down a little bit of a description of what I've just sort of said out loud. So we know sine x, I'll call it y equals sine x oscillates It's a good word for you today. Oscillates between -1 and 1. Okay? But n goes to infinity in the denominator. Thus, the limit equals 0. But why? So I need to talk to you about the but why, and that's the lead-in to the next theorem. Okay? It seems intuitively to make sense, right? Intuitively, this seems like, sure, it should go to 0, but why? Well, the reason is because of something called, oh goodness, I had 2 more. Oh, did I skip it? Oh, it was the bottom of the screen. Sorry, I didn't see it there. The squeeze theorem. So the squeeze theorem talks about this exact thing. It says, if the limit as n goes to infinity of a sub n is L, and it's equal to b sub n, and there exists an n such that a sub n is less than or equal to b sub n is less than or equal to c sub n, then the limit as n goes to infinity of c sub n is L. And I'm going to show you how that works on that previous problem, essentially. Okay? So to apply the squeeze theorem, we need 2 sequences that converge. We'll say both converge. To some value, I guess in the same value. And we squeeze around our sequence. Okay, we said sign goes between -1 and +1. We're going to write that in an inequality notation. So I'm going to go back up because I have more space on the line above. You have more space probably still on your line below, but write it wherever you'd like. But here's the deal. -1 is less than or equal to sine of n is less than or equal to 1. Correct? It goes between -1 and 1. This is the inequality that says that, correct? What I'd like to do is to divide each of those pieces. Oh, let me just say, so -1 and 1 are constants, right? But I can actually take each of these and divide them now by n, which is fine and will not adjust, it will not affect the inequality direction unless I were dividing by a negative, but I'm not. N is a positive number, right? It's the natural number, so this is okay. And then what I'm going to do is I'm going to put the limit in front of each of them. So the limit from -1 over n as n goes to infinity will be less than or equal to the limit n to infinity of sine n over n, which will be less than or equal to the limit of n to infinity of 1 over n. These limits are all going to make sense. I mean, not make sense. They're all going to be in the same order. Like I haven't adjusted the order. I'm taking the limit of each of the values. But here's the cool thing. What's the limit of -1 over n as n goes to infinity? It's 0. And what's the limit of 1 over n as n goes to infinity? It's 0. And the thing we're looking for is sandwiched or squeezed in between. So I need to have a value that's both bigger than or equal to 0 and smaller than or equal to 0, and I'm out of options. It's got to be 0. There's no space. I'm squeezing the space around it. And if you take a look at the graph of this, as in you look at sine of x over x, what you'll see is you'll see your oscillating trig graph that tapers off around the origin. Not origin, around the x-axis, right? It's a decreasing kind of a graph. It squeezes itself around what you're doing. This tells us that the limit as n goes to infinity of sine of n over n is equal to 0. And the justification is this is by the squeeze theorem. Okay, that's how we're going to justify it. It's by the squeeze theorem. Okay, have some more. You ready for number 5 and 6? Yes. Number 5. So, that was the rest of my space for number 4. I guess I did have more space below. I didn't realize it, so sorry. We'll go to 5. All right, so we have a sub n is 4n squared plus 2 over n. So we're going to do the same thing we were doing on the others. We're going to write the limit as n goes to infinity. Gracious. Of 4n squared plus 2 over n. And this is going to be like the first one we did, which was problem number 2. And we're looking for the highest degree exponent, and we're going to divide by it on top and the bottom, okay? So if we divide by 1 over n squared on the top and bottom, I just said divide, I meant multiply, sorry. What do I get on the top? Mm-hmm. 4 plus 2 over n. What do I get on bottom? 1 over n, right? Okay, so, oh, n squared. I left my squared off. Thank you. Okay, everything else look okay? All right, so the limit of 4 is 4. That's fine. What's the limit of 2 over n squared? 0, right? This piece goes to 0. What about the 1 over n? This one goes to 0. So in essence, the limit is approaching something that's got a 4 on top and a 0 on bottom. And we're back to the questions that we were addressing that Ben had earlier. What happens when we try to divide 4 by something that's infinite or by something that's 0 on bottom? This is infinite. So this actually approaches infinity. And this actually means then that this diverges. We should probably have come back up to this first one, then this is converges. I didn't actually write it on the other slide. So number 4 converges, converge to 1. It converged to 0. And then the second one, number 5 here, diverges because it goes to infinity. Okay. It's probably worth noting as well that if you wanted to divide this by 1 over n instead, you'd still get the same kind of thing going on. It would look a little bit different in our work, but it'd be okay. I think it's a little bit more natural to see it divided by the highest exponent every time, so that's my default that I go to. Okay, 6th one. So on this one, there's one thing that you might know to do. This comes into play in chapter 5 in our book, so it's been one of the first things we do in Calc 2. We do have a way to rewrite the numerator of that expression in a little bit more friendly way because it's a log. So using log properties, we could at the very least rewrite this, and how could we rewrite it? 3 natural log of n, right, over 2n. That's fine. It doesn't really help us in answering the question. And the reason it doesn't help us is because this numerator goes to infinity. Not very fast, mind you, but it goes to infinity, and so does the denominator. That's not helpful because I don't have any algebra technique that I can actually use to simplify that. Are y'all with me? So what now? No, but that's a good guess. You're thinking about some of the things that we did in Calc 2 for finding derivatives is what you're thinking of. And we are actually going to go down the road of derivatives here, but we're going to do it by way of talking about limits. And there's a property that we're going to use. It's called L'Hopital's rule. That is not L'Hospital. That is L'Hopital. L'Hopital's rule says the following. If f and g are functions that are differentiable on an open interval AB containing c, except possibly at c itself. We've seen that kind of a phrasing in lots of our definitions, by the way. We're going to assume that the denominator g of x, its derivative, so g prime of x does not equal 0 for all x in AB, except possibly at c itself. So if we're looking for the limit of a function over a function, f of x over g of x, and it's an indeterminate form. So indeterminate form are those very forms that you were asking about earlier. Zeros over zeros. It's also true if you have infinities over infinities, or zeros over infinities, or infinities over zeros. All of these are called indeterminate forms. The ones that pose the most problem are these two, infinity over infinity and 0 over 0. These pose the biggest problem, okay? So when that's the case, I'm going to put that over here, then the limit as n goes to infinity of, they're using x's here. We'll stick with their x's. X goes to infinity of f of x over g of x is the same as the limit as x goes to infinity of f prime of x over g prime of x. This result also applies when we have the other indeterminate forms. I'll write them down here then again, the infinity over infinity. We have also negative infinity over infinity and infinity over negative infinity. So pluses and minuses of infinities. Okay. And it already mentioned 0 over 0. We'll put them all there compact together. All these indeterminate forms. While 0 over infinity and infinity over 0 are also indeterminate forms, or at least they're awkward. They can still determine, they aren't indeterminate, they can still determine which of the limit values you end up having. So going back up to the previous problem then, what that tells us that we can do is we can actually find, so we're looking for the limit as n goes to infinity, and it is helpful to have the rewritten version like this, so we will. And it says that we're able to take the derivative of what's on top and the derivative of what's on bottom. So what is the derivative of 3 natural log of n? 3 over n. And what is the derivative of 2n? 2. And if we needed to, we could continue to use L'Hopital's rule over and over and over again, but you have to stop every time and make sure that it really needs to be used. So right now at the beginning, it needed to be used because it was infinity over infinity, correct? It doesn't have that property anymore. This is now over 2. What happens on the top, though? What is 3 over n as n goes to infinity? That's 0. So now we have 0 over 2. And what is 0? Something that approaches 0 divided by something that's approaching 2. It's 0. Okay? And again, if this were flipped upside down, my answer would be different. So it really matters what's in the numerator and what's in the denominator because they affect the outcome differently, right? The numerator and the denominator affect the outcome differently. Okay, a little bit more, not donations, definitions, the word I want, a little bit more definitions. So a sequence, A sub n, is monotonic when its terms are non-decreasing or non-increasing. Monotonic. It's a very funny phrase to say non-decreasing because you probably look at that and you think, well, isn't non-decreasing increasing? And the answer is maybe. It also could be constant, or at least could have some sequence, some terms within the sequence that are. For example, it could go, 1, 1, 1, 2, 2, 3, 3, 3, 3, 3, 3, 4, 4, 5, 5, 5, 6, 6, 6. Like it can go up like that. It just can't go back down. So as we're looking at these, we're looking at something that's either constant or has some constant terms within it, or it's increasing or decreasing. Okay, that is a monotonic sequence. So generally, you can think to yourself, is this graph increasing? Is this graph decreasing? If so, then it's monotonic. But we do have this sort of variation about the constants showing up in there. And then the next one is about boundedness. So a sequence is bounded above when there is a real number m such that a sub n is less than m for all n. A sequence is bounded below when there is a real number n such that n is smaller or equal to a sub n for all n. Capital M is called the upper bound. Capital N is called the lower bound. And when we have an upper and a lower bound, we say the sequence is bounded. So the example where we did before with sine is a bounded sequence, sine of n, because it kept going bounding up by 1 and it was bounded below by negative 1. It kept bouncing up and down between 1 and negative 1, right? That's a bounded sequence. Okay? A graph that's not bounded is the natural log of n. Because the natural log of n, while it's very slowly increasing, it does increase forever without bound. Okay, so we've seen some that do, and we've seen some that don't have this property, boundedness. Another way you can think about it with some of our graphs especially is, does it have a horizontal asymptote? Right, so if you're thinking about rational functions, some of our rational functions, so you were asking Connor about those rational function details that we saw back in Calc 1 as well. Horizontal asymptotes provide a bound. They're a limit, right? They're a bounding place beyond which we cannot exceed or either go up further or down further on horizontal asymptotes. Those create bounds. So we're going to be determining whether a sequence is monotonic and or bounded. And while these two things are similar, they don't have to be the same. You can be monotonic and not bounded. Okay, that's the example of log. It's monotonic, it's always increasing, it does not have a bound. Or you can be bounded and not monotonic, and that's my example of sine. Sine bounced up and down, it's not monotonic, but it's bounded, doesn't get higher than 1, doesn't go lower than -1. So these are not the same thing. But finding out which one it is not exactly a straightforward process. The confirming graphically is going to be the intuition that you have by doing this. So you're going to have some intuition in doing this. Let's actually start with the intuition of what you expect to happen first, because that's what you're going to do on your homework anyway. You're going to look at this and you're going to say, I don't know, give me my calculator, aren't you? That's what I would do. Grab your calculator. I want you to graph this. I want you to graph x minus 1 over x plus 1. Okay? And remember, we're only looking from, in this case, x equals 1 and on, because x is representing our n. You're looking at something that's continuous, right? It's going to have continuous x values. This really doesn't. These are discrete values. They're points, right? Individual points. But it still should give you some kind of an intuition of what's going to be happening. So if you want your window to be reasonable, at least make your window start at like 1, because n equal 1 or x equal 1 is your starting spot, and then go to 10, and then you can just do your negative 10 to 10 for now, I think is probably okay. Okay. My window looks really cramped, but it looks kind of like this. Yours look like that? Yeses or nos? Something like this? Sophia says no. Okay, I think I have mine in right, so let me just check yours before I go on. Yeah, because your windows are different. So what's your Y min and Y max, Sophia? For Y min and max?
Yeah.
Are you sure? What's your X min and max? Yeah. So this is my graph starting at 1. If you continue the graph where you guys are, it looks like this and like this. Is that fair? But my graph is actually supposed to start at 1 and move this way.
Okay.
Okay, are we good? Okay. Looking at this graph, does it look like it's monotonic? Monotonic means it's continually increasing or continually decreasing. It looks like it is. Does it look like it's bounded? Yeah, it looks like it might be bounded. It's certainly not increasing very quickly, correct? But logs don't increase very quickly either. So it's hard to say for sure based on just the graph. If you base it on knowing some things about horizontal asymptotes, it is okay to say that. There is a horizontal asymptote happening, at 1. I don't have mine drawn very well. But there is a horizontal asymptote at y equal 1 happening. This is bounded. This is monotonic. But we need to actually justify why. So having sort of a perspective from the graph of what we're aiming toward can sometimes be helpful. Let me show you how we justify this. we're going to take a look at what happens at n plus 1. So if I put in n plus 1 here, I get n over n plus 2. Y'all good with that? Okay. If this is increasing, then this value is bigger than a sub n, right? A2 should be bigger than A1. A7 should be bigger than A6. That's what it would mean to be increasing. And from our graph, our anticipation is that it is, in fact, an increasing graph. So we're going to justify that it is by comparing A sub n plus 1 to A sub n. And we're going to compare them in terms of a fraction. Fractions are ratios. Ratios do a good job of comparison for us. Well, our numerator is the one we just found, n over n plus 2. Our denominator is the thing we started with, which was n minus 1 over n plus 1. Okay, so far so good? Fraction over fraction, that's called a complex fraction, and we're going to actually flip that around and simplify it. So we have n plus 2, n over n plus 2 times n plus 1 over n minus 1. Okay, cleaning this up, this gives me n squared plus n over, and look, this should be n squared, let's see, minus plus n minus 2. Did I get it right? I think so. Now, this looks funny, and I'm about to do something that's going to feel a little bit funnier. Are you with me? The numerator and the denominator of this are almost the same thing, right? The only difference is this little minus 2 at the back. Correct? Okay. So what I'm going to do is I'm going to take n squared plus n, and I'm just going to add a minus 2 on top. Now, hopefully you're looking at that and you're saying, Dr. Hand, you can't just go subtracting 2 on top. That's not going to be equal. So I'm going to balance it. I'm going to balance it by putting a positive 2 on a second fraction. Why? Here's the why. What is this quantity? It's 1, isn't it? This is 1 now, plus 2 over n squared plus n minus 2. And remember, all of this was set up to be a sub n plus 1 over a sub n. Are we okay so far? Okay. Well, this is 1 plus something that's bigger than 1. Bigger than 0, so I meant to say, sorry, bigger than 0. It's positive. So when I add the number 1 to something that's bigger than the number 1, I'm going to get something bigger than the number 1. So this thing right here, this expression right here, is greater than 1. Agreed? That's bigger than 1. So now I have, not limit, a sub n plus 1 over a sub n, and it's bigger than 1. I changed this into an inequality. It's larger than 1, and we're going to multiply by a sub n on both sides. And what does our statement now say? Well, it now says that a sub n plus 1 is bigger than a sub n. That's what we were trying to show, that every term was bigger than the one before, right? This means that this is an increasing sequence. It's an increasing sequence. Every subsequent term is bigger than the one before. So there's nothing special about a sub n plus 1 and a sub n, but this is telling you it's just one bigger. So a7 is bigger than a6, and a20 is bigger than a19, and a150 is bigger than a149. Yeah?
Could we prove that by testing them into values for n?
That's a really good question, and the answer is no. So what you might remember from probably geometry is that when we test specific values, those are case examples, and all it takes for something to be wrong is for you to have one value that doesn't work, which means you can't ever prove anything by example.
So that's a limiting factor.
Yes. So this actually is a legitimate proof. This is a proof of this, okay? So it's increasing, hence that means it's monotonic. We haven't done the bounded part, so let me actually do that real quick. I think we have time. I don't like this screen, but it's going to just have to be what it is. So when n is equal to 1, excuse me, a sub 1 is equal to 0 over 2. I just get that by plugging the numbers in, okay? So we're going to get 0 over 2. This is equal to 0. So a sub n is bounded below. Okay, it's the smallest thing. Every term is bigger than it. I just showed that the first one has the bounded below feature because the first value has a number. It's not infinity or negative infinity in this case. So it is bounded below. And then if we do the same thing when we were looking at before, a sub n is n minus 1 over n plus 1. I'm going to do some adjustments to show that this is going to work first. The first adjustment that I'm going to do is I'm just going to remove that minus 1 on top. If I take a subtraction 1 off, it made it bigger. True?
Yes.
N is bigger than n plus 1. If I take an addition of 1 off bottom, it also makes it bigger because I'm dividing by something smaller. Think in your terms of like some actual examples. If I divide by 5 and if I divide by 4, right? If I divide by something bigger, it gets smaller. So this one's going to be bigger. So I've got n over n. And what is n over n? It's 1. So a sub n is less than 1 if you go from the left all the way to the right. So a sub n is between 0 and 1. Hence, a sub n is bounded. And we already did the graph that supported this intuition that we just proved. Okay, so this is a legitimate proof. It really is. We haven't done a lot of that. We're going to see some more of it here in chapter 9. And that's it for today.